All right, my name is Grant Person. My major is nanotech.
I'm Kyle Thomas. I'm in cyber gaming.
And our project is called the Virtual Surgeon, the future of non-invasive microsurgery. Basically, our goal was to try to establish some sort of non-invasive medical treatment system using internal injectable nanobots and a VR system to control them.
So our objective was to determine the feasibility of having remote controlled nanobots for simple microscopic surgeries and having some form of non-invasive treatment for conditions that now at the current time are almost untreatable. And the hypothesis was that the technologies like the virtual reality, nanoscale swarm, robotics, and nanomaterials could be used to create a system for doctors to remotely control the nanobots and remove any of the diseases and leave the patient with a cured treatment.
Now, for controlling the nanobots, first we're looking for a system that actually set up a 3D kind of sort of virtual patient for the surgeon to operate within. And we found that by overlaying CT and MRI scans, you can actually create like an image just like this. And using 3D modeling, you can create the virtual patient that the doctor, using a virtual reality headset similar to like you see Oculus Rift, can operate and remove, or send instructions to the nanobots. Now, for controlling the nanobots, the doctor's instructions basically is actually carried out within his virtual operating room. Will be sent to the nanobots, and then it will be communicated through some sort of kind of a command and control wireless hub that sends instructions to all the nanobots to the nanobots swarm to guide their actions to basically carry out those same actions from within the body. And finding power, powering something the size of a blood cell is really difficult. And so we're planning on using the thermal heat of the body as a source of energy. And so there's Rob Nagel designed a nanoscale engine that uses a single ion, similar to like a piston. And so what we do is we would absorb the thermal heat of the body, use it, focus it, and heat up this ion. And basically what you do is you create like a sort of temper differential, cold and hot temperature zones. And you use this to move the ion kind of like a piston, similar to what you would see in a larger scale Carnot engine. And to move it, it would be propelled by frictionless nanorotors. This is actually pretty cool. This is an actual image of a, let's see, I think it's a cobalt nanorotor rotating within a parasexyphenyl dicarbonitrile nanomesh. Now this is about the size of like a hexane molecule, so it's very, very tiny. You can have an array of these that when they're thermally excited can be somewhat controlled and give you some sort of push and some sort of control over the movement at the nanoscale.
It pushes the molecule. It just pushes the molecule.
Well, yeah, it pushes the molecule.
So the big decision when we were coming up with our project was whether we wanted to create one nanobot that would be able to do everything, or if we wanted to develop a swarm of multiple robots that all have their own specialized purposes. And we chose to go with the swarm because it offered the most adaptability in our surgeries. So having a swarm would allow you to take care of a lot more different types of diseases than just having one single robot. So for instance, some of the nanobots in the swarm would have the cameras so the doctor could see what was visually happening inside the body. Some other of the robots would have cutting abilities to be able to remove any of the like cancer cells or plaque from the neurons of the brain. Some of the nanobots would be able to deliver drugs if the surgery required an anesthetic, even in a very small area. And then we would have one of the nanobots in the swarm that we would send the instructions to that would communicate the instructions to the rest of the nanobots. And this will allow them to kind of locate themselves, and you would know where all of them are at once within the body. Applications for these nanobots would be, of course, to use it for cancer, being able to get down to the microscopic level and just cut it out completely. And Alzheimer's, there was a study done recently where they injected a drug into a patient with Alzheimer's that would remove the plaque from the neurons surrounding the brain, or the neurons in the brain, and they found that it did improve the patient's ability to remember and ability to perform. And if you're able to send physical robots in there, that would actually just remove that plaque physically, you'd be able to have the same effect. And with the cancer cell, you can also do that with the osteoporosis, removing any buildup in the veins that could lead to heart attacks or strokes. And then just lots of other nanosurgery that, for other applications that we haven't really come across yet.
All right, okay, question.
Yes, sir, in the back.
So, if I was understanding you correctly, the power for these nanobots would
Yeah.
be created by cold and hot regions? Is that what?
Yeah, the technical way that they were doing it was, let's see, it was ion held within a modified linear Paul trap, and it uses cooling to establish cold and hot reservoirs, and the temperate differential creates a thermodynamic cycle similar to a nanoscale car engine.
How do you create cold and hot cycles within a system that's notorious for thermal homeostasis?
Oh, wow.
I think that was my question too, because that's, I think, very difficult, because the body,
Yeah.
that's always the thing of the body, is it always tries to stabilize.
It's-
You get a fever, it tries to cool it down. If you're cold, it tries to heat it up. So yeah, that was also my
Yeah, I know for the engine, they did a proof of concept for where they could create like they could control the ion and move it back and forth within a controlled environment, but it would be
right.
going from that to implementing
Specific
into.
area.
Yeah, I would call the human body the only thing that controls the human body is the human body. It's an uncontrolled environment. So you gotta figure that major obstacle out before you.
Yeah. Well, there's also alternative, some of the alternatives were just burning, just using graphene to burn, I think it was some sort of ethanol, just as a simple chemical reaction to power it instead, but I'd have to look into alternatives. So it's,
Okay.
That's a very, that's the part that would be very challenging on the design. The other thing too is, so I would assume that you're injecting this through the bloodstream, correct?
yes.
When you got your swarm,
Yes.
right? So first off, your bot, you're putting a camera, or you're putting, how small is the bot, and how are you going to be able to assemble something with a camera that tiny?
Well, the way we're thinking about for the visual aspect of it would be more like a kind of like a composite image where each nanobot would only generate an image about the size of a pixel or something along that size, rather than requiring an entire camera to be built into it, or something a little simpler.
Okay. Well, because again, I don't have any idea when it comes to how the camera is assembled and all that. I'm just wondering, like, I've never seen a camera that tiny, right? That can, even the endoscopes that they use to put in your system now, that the doctors are using, it's still quite huge, right? And it goes to the tube, not in the bloodstream. Now, bloodstream, you have capillaries, and that are like, the diameter is just so tiny, and so that's that's the kind of thing that that might be a challenge again.
Well, at the moment, the biggest challenges with our project is our technological advancement.
Right.
We're not just advanced enough to create some of the subjects that we covered.
Definitely, yeah.
Most
And
of
so,
the stuff was just proof of concept stuff.
right. And so I guess as you go, because again, designing and all of that is going to be a challenge, right? Because you don't have that much idea yet of some of the very important things that you need to consider. But I think these are the key things now that you have to limit now, as far as, okay, what would be, in terms of maybe designing, instead of getting into the swarm itself at this point, maybe concentrate on one bot and say, how is this one bot, just this, for example, doing the camera thing, right? Even just that. Drug delivery is another aspect, right? I think you can focus this to a much more focused, concept there, and design the bot according to that function. Then you'll have better, I think, target. Because the other thing also, apart from that, is the size of your bot and all that. And your body is designed with antibodies, right? Which, whenever it detects something that's alien, it will just go in there and start
There actually was
corrupting
a
it.
pretty clever thing we came across when looking at that issue. It was, they found a way to disguise certain nanoparticles
To cold it.
with coated like a virus,
Correct.
virus type membrane, so they can avoid the antibodies.
Yeah, so that's one of the suggestions I would have, is that when you design your bot, you make sure that your antibodies don't actually recognize that as alien. So you have to fool your system to
Yeah.
make sure that it doesn't recognize it. And then the other thing is, of course, because you're having cobalt, for example, if you can actually make this work where you have
Yeah.
cobalt as your motor, right, to go in there. Now, you don't want a lot of cobalt in your system either, right? Okay, you're curing the cancer and now you have deposits of cobalt because you have your bots in there. So I think the other challenge is, how are you going to get rid of your bot
Yeah.
after it does its job, right?
I mean, ideally with the bots being that small, they hopefully will just be able to maintain their form as they get passed through the kidneys. It just,
Yeah.
Oh, that you want to flush.
You could have issues with the body embedding it into recognizing it as a foreign element or some type of.
Right, because if it now recognizes it's my body here, I'm gonna keep this, right? And then now your kidney is not. So I guess one key point is, after it does its job, that you have a catalytic enzyme attached
Yeah.
to your whatever coating, that once it releases its job, it changes the conformation, that it actually will remove the covering. Now your antibody gets to recognize it as alien
Yeah.
and starts just getting rid of it, right? Then, yeah, so it's a molecular design that you can, if you can design the bot, you should be able to incorporate that, I think, in that system.
And I think that if motility is an issue, you want to kind of take a biomimicry kind of approach. The body already has movement. There's constant movement in the body. Utilize it and think about it as a vehicle in and of itself. A way of it's like the tubes that you put your bank statements up in. You know what I mean? It's the same thing. Use that instead of trying to make engines out of thermal displacement.
Right, maybe it can cling onto one of your blood cells.
One idea.
Instead of, just make it cling into one of your blood cells, have a bridge, molecular bridge, right?
One idea that we discussed was having the nanobots flow just in your veins and then just adheres to the wall of your vein while it's doing whatever it needs to do.
Using
And then
something like the
detach it.
It's like the plant, You can do that too.
Also with the cameras, another idea that we discussed, but we weren't really sure how we would execute it, was using that central hub that's already going to be there for the communication as kind of an echolocation sort of system, so they can still know what's going on around them, just not through visual imaging. It's going to be through communication.
Right. Yeah, so, those concepts, you can put it together and then design the actual bot. Conceptually. Again, it's conceptual. There's no limit in concepts, right? So, just focus on probably even one bot that does that job. If you really concentrate on imaging or drug delivery, however it is, put those suggestions and you should have a good conceptual bot at the end, right? All right, any other questions? Yes?
What were your names again?
Grant.
And that's Thomas.
That's,
Kyle Thomas.
Kyle Thomas.
Because there's 2 Kyle T's in here.
Right, I know. That's why I would rather have the Thomas, not Kyle, because there's another Kyle. All right, so we're good. Thank you both. Very good presentations here.